Here are your products again. We're looking at details. Let's do this one down here. What'd you get for this one? We have a secondary alcohol. That's one of the big three. What's that going to do? Christopher? Christopher, right? Yep. Should it oxidize? What's the product? Secondary alcohols have oxidized to what? Ketone. Right up top. Right? Got two H's here. They essentially get removed. All right. The mechanism is not plucking out two H's. We haven't looked at the mechanism yet. But essentially, two get removed, double bond forms between C and the O. Ketone. Boom. How about the product below? On the line, what type of reagent do we have? You got to recognize that's an oxidizing agent. It's a metal with lots of oxygen. It's very common, a metal oxidizing agent. You got an alcohol. Alcohols get oxidized by the big three. That's one of them. So that's what you're doing here, oxidation. What's the product? Primary alcohol gets oxidized to what? Aldehyde, but it will then get further oxidized to the carboxylic acid. So the product here is carboxylic acid. Please keep the string number of carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We don't lose carbons. Many of you on the quiz is losing carbons. You need to make sure you don't lose carbons. What's the intermediate here that's not isolated? We've already said it. Aldehyde, but then it gets further oxidized. It's right up top, right? We just got a specific example. Big three. With the big three, you cannot stop at the aldehyde. The big three take primary alcohols all the way. The big three do. Maybe something else doesn't. Maybe calcium hypochlorite doesn't. That's what we're using in lab. But the big three do. The big three take the primary alcohol all the way to the carboxylic acid. If you want to stop at the aldehyde, we can do that. We'll talk about it below. Okay, we've talked about everything up there. Let's look back. By the way, the green sheet, everybody has a green sheet. See where you're at? Keep that handy up. That's your outline. What color is the other six? White is oxidation of alcohols. So we look at some of the redox, chromium. Color change can be used as a test. What type of alcohols give a positive Jones oxidation test? Positive means you get a color change, like something happened. Primary and secondary. Tertiaries do not, because tertiaries can't be oxidized, and thus tertiary alcohols can't serve as reducing agents. There's a note here. Aldehydes also give a positive Jones. No textbook's probably going to take time to tell you that. But think about it. Does chromic acid oxidize an aldehyde? No, we just got through talking about that. The aldehyde is not isolated, it's further oxidized. So you actually get a redox reaction with an aldehyde also. Right? Does that make sense? Let me give you a very brief idea of mechanism, okay? You may not even want to write it down. Just so it's not magic. Let's just give us an alcohol here, all right? And if we oxidize this, we'll get the ketone. We're using metal reagents. Instead of showing chromium or permanganate, I'm just going to show metal. And the metal is going to have a charge. And so let's just say M+, very generic. What can happen here is these electrons can sort of bond to the metal, just like to a proton. And that gives what? OH metal. Still lone pair. It's like we protonated the oxygen, but we're complexing with a metal. Let's do this. The electrons I circle, let's keep track of them and see where they are when we get done. Now at this point, what do we need to accomplish? We need to remove an H, put in a double bond. Well, you also have water around, something that serves as a base. These electrons can take the H, these electrons can move in here, make pi bond, and then kick off the metal. What does this arrow movement give? Well, it gives double bond. There is an H here, plus charge. A lot of people need to work on identifying charges in your mechanisms. Some of you just need to work on understanding what an arrow is and mechanisms. That, we also make H3O plus, and then the metal. But what does this arrow mean? These two electrons are doing what? Moving on to the metal as it leaves. So now the metal has two electrons. So these two electrons are now gone, and where are they at now? The metal now has them. The metal got reduced. This lost electrons, so it got oxidized. Now there's lots of things that can do this. You can also oxidize alcohols with just chlorine. That's because this attacks the chlorine and gives you, it makes an OCl bond, and then you do the elimination, kick off the Cl, and it takes the electrons. Now this looks like an E2. Organic 1, we learned E2 requires a strong base. Well, that's not a strong base. Well, that's because we were talking about making carbon-carbon double bonds. Here, because we're making carbon-oxygen, that's a much stronger bond arrangement, you can do this. Where you can't do it for carbon-carbon alkenes. Okay? Does it look less like magic? More like a reasonable something? All right. Now let's see where we're at. Okay. If you want to stop at the aldehyde with primary alcohols, that can be done. Not with the big three. And this is on both sheets. We're on the purple, we're down at the bottom. Kind of go back and forth here. PCC should be in your textbook, or it's defined somewhere here, maybe on the other page, probably. Pyridinium chlorochromate. It's actually another chromium reagent. Okay, structure's on the other page. The main thing is, if you look back up there, what do we need to go from aldehyde to carboxylic acid? And do it on the reaction arrow. Water. If you include water, it's going to continue on. If you don't include water, it can't continue on. This is going to be dry. Okay? Now, the big three, you can't use dry. They don't dissolve in dichloromethane. You have to have water to do the chemistry with it. PCC is a chromium reagent that will dissolve in an organic solvent without you having to use water. And because there's no water there, it can't go all the way to the carboxylic acid. It has to just stop at what we showed as an intermediate up there, just the double bond O. Now, I like to draw in the H of my aldehydes. One H remains after you remove two. Okay? So PCC. In the old textbooks, there were other variations of this, one called PDC, also Collins reagent. Actually, these may be the same thing. At this point, you don't see those terms as much, but it may show up somewhere. So I just put it in there to be complete. Is there PCC on the other page? Yeah. In the middle there, right here. It's pyridinium chlorochromate. Pyridinium is a protonated pyridine, and then you've got this. You can show a loose structure. It's basically a combination of pyridine, ACl, and chromium trioxide. And so I just show it again over here. You take this alcohol with one of the big three, you get the carboxylic acid. But if you do it with PCC, dichloromethane is a common solvent, dry, you can get the aldehyde. Of course, aldehydes are further susceptible to oxidation. This can be done with big 3. Big 3 will take this to that. But we also have another reagent that will do that. Silver ion. I don't know that silver ion is ever used in organic chemistry other than right here. Silver ion is a very common reagent for taking aldehydes and oxidizing them to carboxylic acids. It won't oxidize alcohols, but it'll do this conversion. And as it oxidizes the aldehyde, something has to get reduced. The silver ion gets reduced from +1 to 0, which is silver metal. And the silver metal will appear in your flask, and it will look like a mirror. Because it's just metallic, and you can almost see your reflection in there. And it's often called a silver mirror. And that's actually another chemical test for aldehydes, and it's called the Tollens test. Using silver as the Tollens reagent, Tollens test. Aldehydes give a positive Tollens test. You add the reagent, you get the silver form. That's positive. Ketones do not, because ketones can't be further oxidized. So the Tollens is a way to distinguish an aldehyde from a ketone. And that's all explained over there. This is just another review. Of course, you take a secondary alcohol. This is one of the big 3. What do you get? Just ketone. Ketones can't be further oxidized. Any questions about the stopping at the aldehyde? And then we have a separate possible oxidation. It can be done with the big 3, of course. Or we have the silver ion, the Tollens. By the way, the ammonium hydroxide is used to help solubilize the silver. Silver salts are not that soluble in water. Complexing with ammonium hydroxide helps solubilize it. That's just the role of that. Questions? Once again, guys, you're not going to learn all this boom right there when I tell them to. The idea is that you look at this ahead of time. Now you're getting some things answered, clarified, and then you go back and, of course, look at it many more times. Okay? Questions about oxidizing alcohol? We pretty much covered it. Very important. Wasn't there a warm-up? I mean, you guys see the importance of this, estradiol to estrone, secondary alcohol going to ketone. Questions about oxidizing alcohols? Does a tertiary alcohol give a positive or negative Lucas test? We covered Lucas. Okay. Tertiary alcohol, positive or negative Jones test? Negative. Negative. What about Lucas? Tertiary alcohol, positive or negative Tollens test? Ketones, positive or negative Tollens test? Hopefully you also understand why. Okay. So from the green sheet, we did the alcohol oxidations. I think we covered everything. The last topic on the green sheet is oxidation of alkenes. Again, I think Dr. Adele maybe covers a number of these. Organic 1, I do not. So for my guys, this is new stuff. Organic 1. The overview is right here. Starting with this model alkene, we're going to do oxidation reactions. The first sequence of reactions is going to form a diol. Where essentially we're going to put two OHs on the alkene carbons. Get a diol. How do we know it's an oxidation? Well, how many bonds to a more electronegative atom does that carbon have? None. How many does it have now? Now bonded to an oxygen. That's 1. Okay? Been oxidized. Both carbons have been oxidized. We say the alkene's been oxidized. We'll see the reagents that do this. There's 2 different reagents. One of them is quite toxic but gives high yield. The other is not that toxic but gives low yield. So we'll have to say, which one do you want to use? Toxic high yield? Not toxic low yield. Another reaction will be what we call ozonolysis. We're going to use ozone, followed by kind of a magic step. This is going to cleave the alkene. The 2 alkene carbons are actually cleaved. And both carbons become carbonyls. Carbon now has 2 bonds to a more electronegative atom. This is the 2 carbons. In this example, we have a ring, and so when you cleave this, it opens up, both become carbonyls, that's your product. You can also do this with KMnO4. There's a little bit of difference here because aldehydes do not survive with KMnO4. That's one of the big 3. The big 3 oxidized aldehydes, so it would go to the carboxylic acid. Ozone, you can stop at the aldehyde. If you want to go to the acid, you have to do a different reaction. So that's kind of the overview. Let's first look at the diol chemistry. This is in the purple. And also the white. Purple is sort of just the outline. The white is more where we're going to see the chemistry, the mechanism. First thing is going to be, we're going to oxidize an alkene to a cis-vicinal diol. A slang name for that is a glycol. You probably know ethylene glycol, which is antifreeze. That's a diol. And it's vicinal. You should know what cis means. What does vicinal mean? Vicinal means they're going to be next door to each other. Okay? They're like neighbors. They're in the same vicinity. But they're not on the same carbon. First way we're going to do is with KMnO4 under mild conditions. Then we'll look at using osmium tetroxide. Let's first look at KMnO4. We can go to the other page here. So you take this alkene, KMnO4, mild and cold, that'll be important. Usually this is done under basic conditions. You might have learned in Gen Chem, when KMnO4 is much more stronger oxidizer under acidic conditions. So to keep it kind of mild, you use basic conditions. We can get this, first off, it's a diol, yeah? It's vicinal, which typically means 1,2, and it's also cis. So that's all in the title there. Now you may also get an enantiomer if applicable, but there's no enantiomer of this, right? No enantiomer. Let's look at this mechanism. We see, I got like 3 or 4 Seans and 3 or 4 Britneys. I can't. Is it Sean? Okay. Tell me if you can't see, okay?
Oh, yeah, I can see.
All right, here's KMnO4. Lewis structure, of course. You've got to be able to draw Lewis structures in organic chemistry. There's a K plus sitting with this minus. These reactions are they're concerted and they're somewhat similar to like a Diels-Alder. High electrons, I already got the arrow moving here. Move and attack the oxygen. These electrons move on to the manganese and become a lone pair. They should. Why not draw a lone pair then? I think I remember that. Always have to put a lone pair there. So that's what that arrow means. What? Did anybody get a WDAM on their quiz? That means, what does arrow mean? If you're using arrows and I don't know what you mean, if it doesn't make sense, I'll write WDAM. What does arrow mean? I have one student, he called it a wadam. But I just say WDAM. Okay? What does this arrow mean? It looks to me like the electrons are moving on to the manganese, and instead of being a bonding pair, they're now a lone pair. This carbon is making a bond. Here we go. Boom, make bonds. Now we have a bond here. There's that bond. Moving on, lone pair. What does this mean? These electrons are moving out and making a bond here. These are, okay. So we make those 2 bonds and manganese gets a lone pair. And this is a kind of a concerted cycloaddition. Somewhat analogous to a Diels-Alder. Oh, that's a 4 plus 2. This is sort of a 3 plus 2. Now that's called a manganate ester. It's not stable. But the most important thing, now we have 2 oxygens on the 2 carbons. At this point, this is not stable. With water, that gets cleaved. This becomes OHs. We're just going to call this magic. Okay? We're not going to look at the mechanism. Okay? It gets cleaved. That becomes MnO2. And game over. Now look at the manganese. Here it's manganese 7. If you could do a redox for manganese. What is the oxidation state now? That's a 4. The manganese has been reduced, yeah? From 7 to 4. I mean something got oxidized. What got oxidized? The alkene. Okay? There you go. Why cold or mild? Because if you do this with heat, or you include acid, which makes it more reactive, you'll cleave the carbon-carbon bonds. We'll do that a little bit later. This is a stereospecific concerted addition. Why do you get cis? It's because here's the alkene walking along. That's planar. Here's the KMnO4. Okay? Hold out your oxygen. Your other one. You got 2. Hold them both out. Okay. I like that oxygen. We could maybe try to explain why. It might be questionable, but go with it. Okay. I'm going to like that oxygen, and so I'm going to attack. But at the same time I attack you, you attack here. Boom. And it all happens at the same time. Now the 2 bonds we just made, are they on the same side or opposite? They got to be on the same side. How are you going to throw a curveball and bond over here? Everything happens on one face. That's why it's both bold. You can also show this both dashed. But see, if you showed the product both dashed, it'd be the same thing, because it's not chiral. But when you do have chirality, that's how you get the other enantiomer. Whether you attack either side of your alkene. Okay, so show the product of this reaction right here. All I did was add a methyl. KMnO4 cold. there'll be lots of reactions in organic too. First thing you have to do is say, okay, what do I have here? I've got an alkene, I got KMnO4, what am I doing? Looks like an alkene oxidation. Okay, the next step is, well, what's going to be the product? It's going to be a cis-diol, right? Okay, now, what type of stereochemistry do I expect for the cis-diol? Well, I said cis, right? This is the thought process. But you can't just think about it once, you have to think about it until it becomes... Somebody have product? OH, OH, methyl is going to be back, right? Plus what? Plus an enantiomer, because this is chiral. What will the enantiomer look like? That's where both OHs are back, and the methyl's forward, right? Chemistry can take place from the front side or the back side. Front side or the back side. Question. This is a transdiol. How would you make a transdiol from, well, not from that, we don't have a methyl. How would you make a transdiol from that? How would you do that? We've already seen it. We saw it earlier this week, or the past couple of days. Somebody figure out how you would do a transdiol. All right. Tomorrow morning when you're watching the Super Friends, they still come on? Y'all don't even know the Super Friends. When I was in 4th grade, I watched Super Friends. 8 o'clock on Saturday morning.
Is that like Power Rangers?
No, this is Batman and Robin and Aquaman. Wonder Twins, they came on a little later. No, get ready to... And on Saturday morning, I was up before dawn watching cartoons. All right. Now, we can also do this using osmium tetroxide. Analogous to MnO4, but MnO4 is an anion. OSO4 is neutral. See, OS should have one more electron. With one more electron, it's neutral. With manganese, if you give it the extra electron, it's a minus. Mechanism is the same thing. I mean, it's still a similar reagent. Inserted. You get the osmate ester. Now, the osmate ester is actually stable. That can be isolated. Just like before, we have to have a second group of reagents to cleave the osmate ester to the diol. That can be done using either hydrogen peroxide, which is an oxidant, or sodium hydrosulfite, or sodium bisulfite. That's actually a reducing agent. So it's very different mechanisms, but both will cleave it, and we're just going to call it magic. So it's not worth us looking into because it's so off the wall. Okay. So I just call this a magic step. So it does the same thing as the mild KMnO4, but it actually does it in better yield. Because KMnO4 has a tendency to cleave the carbons and get something else. Osmium won't cleave. Problem though, osmium is very toxic. It's actually on the list of like terror chemicals or something. So we won't be using osmium in the lab next week. But people have used it because they like to get good yields. And, some examples. So we have osmium and then a magic step. What are we doing here? Making a diol. Have an alkene. We get this diol. Of course, if you showed them both back, that's the same thing because this is not chiral. Right? It's not chiral. Now that's actually an easier one. When you're dealing with rings like the first couple of examples, it's easier to show stereochemistry. When you have a product that has free rotation, you've got to be more careful. I really should have one here. Let me show you the strategy, and then there should be one in the workbook. Okay. Why did we put these two bold? Because we know we're going to cis diol. Okay. But you got to be careful how you do that when you have an enantiomer as possible. I recommend when you do these reactions where, if it's chiral, if you turn your alkene sideways. We did this in organic 1. Okay? Instead of having the alkene on the board planar, turn it like this. So if these two methyls are down, here it is. They're down. If I turn it flat, the two methyls are now what? Coming towards y'all. That's what I'm trying to show here. It's like you can turn flat, now you've got things coming forward and back. But it's still planar, it's just planar this way. Okay? Instead of planar up and down. Now, you turn it, you haven't done any reaction, you just turned it. But now you've set dashed in bold, so you don't have to worry about that from now on. Just by turning it. Now, what does the reagents do? They bring in two OHs to each carbon. If it's like this, they bring them in forward or back. If you turn it like this, it's either straight up or straight down. Now you can bring in the two new H's straight up or straight down. Okay? I really should point one out. Help everyone here. Probably a problem in the workbook. Let's see. I think there's an alkene oxidation page. Does it make sense to turn it first? That gives you your dashed in bold and you don't have to worry about it again. Just by turning your starting material. Please look, I think there's a page of alkene oxidation reaction. There's probably one that's kind of like this. Okay? Please, I recommend turning it. If you don't need to turn it to get the right answer, then do whatever works for you. But for me, I always turn mine. Question?
So you're saying when you turn it, then you don't have to show, just show one part.
Well, the problem here is this: there's no enantiomer here. I mean, this, and so it's. I really should have a different problem. We can look back to that. Please look at the one in the workbook on the alkene oxidation page. Okay? The strategy is to turn it. Everybody clear with the strategy? Question about the strategy? Okay. We do need to think about going backwards, and we'll eventually do multi-step synthesis. Here's a product, guafenicin. If you go to Kroger and buy some decongestant pharmacy today, you're going to get some guafenicin probably. Okay? Well, somebody had to make it. Don't grow on trees. How could you make it using these reagents? What starting material would react with these reagents to give this? Well, what does these reagents give? Diol, right? You see a diol? Yeah. So just show the starting material. I mean, hopefully it's pretty straightforward, especially once you see it. We got this. How about that? Would The osmium reaction converts this to a diol. Now there's no stereochemistry, there's no relative stereochemistry. That's chiral. Of course, it'll be racemic, right? I mean, there's nothing chiral over here that can't be optically active. We can go back even further. How would you make this? Well, let me give you a starting material. What if you had this? That's called phenol. You put a methoxy there, and it's called guaiacol. How would you do that? Well, we need to get an alkyl group on the oxygen. That looks like what type of reaction? Williamson ether. Treat to the base, make the anion, and then you got to come in with what? Maybe sodium hydroxide, and then come in with that. The O- can attack the carbon, kick off the leaving group. You need this to attack the carbon and kick off the leaving group. Yeah, you can buy a big old jug of this. Both of these are dirt cheap. It's quite toxic. And this is toxic. On industry scale, they probably use K-4. In industry, they're probably not going to use osmium. Osmium is used more on small scale, research scale. Questions? Next topic is oxidative cleavage of bisphenol diols. These diols can be cleaved. And they can be cleaved. Essentially, when you cleave it, each carbon then double bonds to the oxygen. And that's what we have here. Each carbon is now double bond to the oxygen, and we separate the two carbons. A reagent that will do that is periodate. Either periodic acid, or you can use sodium periodate, NaIO4B. This reaction is not highly common. And the main reason I cover it is it shows us that these can be cleaved. Periodic acid has a very similar Lewis structure to like osmium tetroxide and K-4. And the first step is forming this periodic ester. Now, instead of an alkene attacking, it's the oxygens attacking. The two oxygens become bonded to the iodine. And I'm not going to show any mechanism here. You do have to lose water. These two react, lose water to make this. At this point, this thing is not stable, and it will break down by an intramolecular process. If you look at what the arrows do, these electrons break away from that carbon and move here. And thus you didn't have a double bond between the oxygen. Something has to leave the oxygen. These move on to iodine. Something has to leave the iodine. These electrons move down, make double bond over here. Something has to leave this carbon. Well, that's the ones that went over there and made the double bond over there. So if you understand your arrow movement, it's all shown here. What does this give? It gives those two products. They're just turned. What does the eye now look like? It's going to look like that. Go through the arrow movement. Make sure you see how it looks like that. Now here, the iodine is +7. Now it's +5. So the iodine's been reduced. The diol has been oxidized. Because now each carbon has two bonds to an electronegative atom, where over here each carbon only has one bond. When you do cleavage reactions, sometimes you're given rings. You have a diol. What does this do to a diol? It's something for a note card. You just got to know. Friday cleaves diols. So we're going to cleave it. What does each carbon become? Each carbon becomes a carbonyl. So this is it. It's been cleaved, and each carbon is now carbonyl. But the top carbon, there's an H there, right? Isn't there an H on that carbon? It's still there. I drew it in, and that's thus an aldehyde. The bottom carbon, is there an H? No. There's a methyl, and it's still there. And because it's there, that's a ketone. And so this is a diol cleavage to two carbonyls. Turns out that one's an aldehyde and one's a ketone. Now this takes us to the third and final reaction. First off, let's go back to an alkene. What did these three reagents do to the alkene if we did them in sequence? What did the first two do? That's the osmium in the magic step, right? What do the first two give? Diol. So let me draw the diol. Nothing is going to happen over here. The diol is going to be cis or trans. I'm going to draw it. No, it's not going to be cis or trans. It's going to be front or back. I'm going to draw it like this. There's also a methyl. Plus what? What else is going to be formed here? Not going to be an enantiomer. I thought that would be the answer. It won't be an enantiomer. What will the other product be? The OHs could be back. Right? This could be forward. What is this going to be? No change. We didn't do any chemistry over there. No change over there. Are those enantiomers? No, those aren't enantiomers. They're diastereomers. This is an example where you don't just memorize it, they get an enantiomer. You have to be able to draw it, look at it, and assess it. Those are actually diastereomers, right? Now, what does peridate do to a diol? Cleaves it. Cleave it, what do you get? You get that. Either one gives the same thing. So this is step 3. So there we're combining multiple steps. So this is the first two we've looked at. Diol and then cleavage. The next thing we're going to look at is a reaction that will do all this sort of on its own. And that is what? You guys, I know you saw this in some of you in Organic 1. Ozone, down at the bottom. Ozone, which is going to be called an ozonolysis. Ozone followed by a magic step. That's going to be magic. We're not going to look at mechanism. That will give the same thing. It will cleave the alkene and give you the two carbonyls. The diol may be an intermediate, but it's never shown. This is alkene cleavage to two carbonyls. It's the same thing as this sequence did. Let's look at this mechanism. You take this alkene, react with ozone followed by a magic step, you get two carbonyls. Just cleave it. It cleaves it, each carbon becomes carbonyl, and if you look at it, that's what you got over there. Mechanism for this. You need to be able to show a Lewis structure for ozone. It's going to be dipolar. You can show this. You can move these electrons here and get this resonance structure with a minus and a plus. At this point, we can do what looks like a Diels-Alder. So it's going to be 3 plus 2. The alkene electrons can attack the plus. And at the same time, this minus attacks here. Hold up your plus and minus, Adrian. Here, I like that plus, okay? So I'm going to break away, but at the same time, your minus is going to run here. Boom, concerted. All happens at the same time, same side, right? Guess what? I turned my alkene. I didn't show it turned here, but I had it turned there. Turn your alkene, right? If you turn it, this R be forward, this H is forward, this R is back, this R is back, right? Now instead of side, I got top or bottom. And it just comes in straight up. Straight up. Everything's straight up here. The new things are straight up. Or I could have drawn it straight down. This is called a malozanide. Anybody know Spanish? What is malozanide? It's actually not M-A-L-O. Malo?
Mal means bad.
Bad. That's a bad ozonide. Okay? It's not stable. It's a bad ozonide. It's not stable because all these oxygens don't like being bonded together. It will rearrange according to this arrow movement, sort of like we saw before with osmium. That arrow movement gives these two. Both are carbonyl compounds, but this has an oxygen on it, that's a carbonyl oxide. A little bit convoluted here. This then reacts again by this arrow movement. You should look at it and follow it. It's all very straightforward. That gives, after this attacking here, these electrons attack here, kick these up because that oxygen needs electrons. We end up with what's just called an ozonide. It's a good ozonide. Still got 3 oxygens, but this rearrangement, only 2 are bonded together instead of all 3. So look at your arrow movement. Ozonides can be isolated. But if you take a magic step, either zinc or dimethyl sulfide, smelly, both of these are reducing agents, it will actually give you your final product. This will be magic for us. I'm not going to show you the mechanism. It will give you what we said it gives you at the top. Each carbon becomes carbonyl. Whatever's on the carbon is okay. That had 2 R's, this had an R to H. That's actually a ketone, that's an aldehyde. Okay? We're about out of time. You can see the resulting products. One of the oxygen ends up on the zinc or something. These are the ones on the back page. Okay? I think that's kind of a summary. Actually, that's where the one was. Do the ones on the back page, please. But please also be doing NMR. I could just work on this like all day.
Most likely move it to Monday after.
See you guys at seminar 1.
Have it out right now.
Products. Yeah. All right, guys.